Hi everyone. So I noticed that a lot of you are struggling with proofs in assignment 1 and assignment 2. So I thought it will be helpful if I did this session or this tutorial on how you go with mathematical proofs in general. This tutorial applied to any mathematical proof actually, so you can use that even for other courses or later assignments. So it's basically general ideas. The first thing is that you can't really prove anything using examples. For example, in assignment 1, I got a couple of theories for people saying stuff like if A equal to such and such, B equal to such and such, then C equal to whatever. And my response to that, this doesn't really prove anything, because how do I know that there is no counter example for the examples you gave? Maybe the example you gave prove that the statement is true. However, there might be another example that the given statement or the things that you are trying to prove is not true. So just like a rule of thumb, don't prove anything using giving examples. That was a quick thought, because I noticed that a lot of you did that. The second thing I wanted to talk about is how I personally go with these kinds of questions. And what I personally do is that I do two steps. First thing is that I start with visualization. I try to visualize the given statement to me, and I also try to visualize what I am trying to prove. After that, I kind of go with the question using some sort of technique that guide my thinking. It's important to know that each proof question is intuitive. Hence, you will have to come up with like your own original idea. There is no fixed steps or process you should go with. However, I think if you understand how these general techniques or guidelines, this might help you a lot. There are tons of ways to prove anything actually in mathematics. However, I think these three I wrote here might be very important for at least for this course. Maybe another one or two might come up in later assignments, and I will do another recording for these. However, let's emphasize on these three since they will cover the first two assignments. I think the third assignment too. So the first technique is that proving by construction. So from its name, proving by construction, you are trying to build or you are trying to construct something. Basically, you are giving some sort of a statement, mathematical statement, and you are trying, and to prove by construction, you are trying to manipulate or use the properties of these given statements to reach a conclusion. A pretty good example for this is the proof in assignment 1. So if we go through that, so you have this question: show that if A, B, and C are sets with A is a subset of B and B is a proper subset of C, then prove A is a proper subset of C. Let's try to visualize that and apply this construction thing on it. So when I see something like that, I start by visualizing A is a subset of B. Hence, I know that either, wait a second. So I know that either A equal to B or A is contained in B, right? A and B. I also know that, or it's given that B is a proper subset of C. Now, the difference between a proper subset and a subset is this equality sign. So if a set is a subset of set, it means that it's either contained on it or it's equal to it. However, if it's only a proper subset, it means that it's only contained in the larger set. To make sense of this, for this particular example, for example, B is a proper subset of C, hence we know that B is only contained in C. It can't be equal to it. Stylus is, yeah, B can't equal to C. So in this particular example, we know that C will contain B. So actually you have two cases, either A and B are equal to each other and both are contained in C, or A is contained in B and B is contained in C. Hence, basically they are the same thing. Actually, they are not two, because in general you have A and B contained in C. Now, what you are trying to prove is that A is a proper subset of C. And if you translate this to a logical statement, you can say that you are trying to say every element in A is contained in C. Just looking at these diagrams, you can naturally see that this is true. So in either cases, if A equal to B, then everything in A is contained in C. If A is contained in B, and B is contained in C, then also everything in A is contained in C. However, you can't just like give these diagrams. You have to use logical statements. Hence comes the construction technique. So what you go is how you go with construction is that you look at the given statements you have, and you try to come up with a way to manipulate the properties of the given statements. And if so, what I was just saying is that if you look at you should look at the given statements and try to use the properties of these statements to reach some sort of a conclusion. So just looking at these randomly, I know that B is a proper subset of C, and what this means in logic is simply that all elements in C, all elements in B are contained in C for all x's. If x is an element of B, this implies that this x element also belongs to C. And it also means that there exists an element x that belongs to C and it doesn't belong to B. By the way, you can negate anything using either this notation or this notation. So this is the same thing as saying this or saying this. This means not in logic. Anyway, so this statement could be translated on the diagram that for all x's, all the x's in B belong to C, and also there is another, because this is an AND, there is another x that belongs to C and doesn't belong to B. Okay, looking at the other statement that A is a is a subset of B, we can translate this in logic to the following statement. Because A is a subset of B, we know that all elements in A also belong to B. if X is an element of A, this implies that X is also an element of B. Now, it should be obvious from these two statements, 1 and 2, that, wait a second. Now, from these two statements, you actually reach the conclusion because anything in B is contained in C, and actually anything in A is contained in B, right? So from 1 and 2, you can say that all element x's, if for all element x's, if x belong to A or is an element of A, this implies that x is also an element of C, right? Because it's an element of B, and B and all things in B are elements of C. Hence, you can just like break this bridge and directly say that if it's in A, then it's in C. It also means that this other part, a lot of you missed that something exists in B, something exists in C, and it doesn't exist in B. And since A is equal to B, or it's contained in it, hence this element contained in C, if it doesn't belong to B, it also doesn't belong to A in these cases. So also here, if you have X, if it doesn't belong to B, it also doesn't belong to A. And that's actually the definition of proper subset. There exists an element in C that is not in A, and all elements in A belong to C. Hence, you just can say that A is a subset of C. Now, just like to recap what we did here, I started by visualization. After that, I just like looked at the given statements, and I wrote down what the logic statements I can like extract from these givens, and naturally you will figure out your way while doing so. Just like by writing these two statements, it should jump to your mind how, by looking at both of these and the diagram, how to like reach the conclusion. So that's it for proving by construction. Proving by construction is the normal way. That's how most of you actually do without thinking about it. So basically, that's the basic way to go with proofs. The second and third techniques, which are contradiction and contraposition, are more interesting actually because they are not very intuitive, or not very intuitive, but let's say not doesn't come naturally. So let's start by an example on proving by contradiction. So the second thing is proving by contradiction. Now, proving by contradiction is a little bit trickier. What you are trying to do here is that you are proving that the opposite of your conclusion is not true. Hence, your conclusion is true. For example, in assignment 2, you had this proof. If A is a subset of B, this implies that A intersection with B complement equal to phi. To prove that, now, first thing you should start by trying to prove this by construction. So spend like actually you can do that, but spend like 5 minutes thinking about it. If you didn't reach a conclusion, then think about another technique, which is contradiction. I will not go through how to do that by construction, but you can actually do that. So what you do in proving by contradiction is that you assume that your conclusion is not true. So in this particular example, you will assume that A and the intersection with B complement does not equal to phi, and you start doing the same thing you did in proving by construction. From this statement, translate it into some sort of a logic statement, and naturally you will find that this leads to some sort of a contradiction that will prove that this is not true. And since this is not true, then it must be, since the intersection does not equal phi, then it must naturally equal to phi. Let's go through that and see how it works. First, I'll start with visualization, as we usually do. So as you can see, A is a subset of B, hence it's either contained in B or it's equal to it. And what we are trying to prove here, that the intersection between A and B complement is phi. You can see this from the diagram, that B complement is anything that is outside of B, and since it's outside of B, then it doesn't intersect with A. You can just see that from the diagram. Now, how to translate this into logical statements? Let's start with what we just said, which is let's assume that the intersection does not equal to phi, and hence the intersection does not equal to phi. This means that there exists an x, or an element x, such that x is an element of A and x is also an element of B complement. The intersection between the two are not phi. Then there must be an element that belong to A and B complement, right? So there exists x that belongs to A and x belongs to B complement. Now, if you look at the diagram again, you can see that there is no element that can satisfy this, right? I mean, if it's in A, it doesn't belong to B complement, and if it's in B complement, it doesn't belong to an A. Here, it needs a little bit of intuition to translate this into a logical statement, which is looking at the first proposition given, We know that A is a subset of B. Let's make this one. Since A is a subset of B, we know that all x's in A are also in B. Now look at these two statements. X is an element of B complement from 1, and from 2, X is an element of B from 2. This is a contradiction. From the definition of a complement, the complement is all the elements that are not in B. So an element can belong to a set and its complement. So we can say that 1 and 2 are contradiction. Hence, the intersection the assumption we started with does not equal to phi is false, and hence this is false, then it must mean that A and B complement equal to phi if we have the proposition. Sorry. If we have the proposition A is a subset of B. So in contradiction, you start by assuming that your conclusion is false, then you fall back to proving by construction. And what you will naturally see is that by assuming this false assumption, this will lead to a contradiction. Hence, this assumption is false, and since this assumption is false, the original assumption is true. So proving by contraposition is kind of the trickiest one. The main idea here is that if you can't prove a statement, then prove its contrapositive, since a statement and its contrapositive are actually logically equivalent, and I will talk about why is that true at the end. So if you have a statement like this, you know that the contrapositive is just like a negated flip. So you just like take your conclusion, the negation of your conclusion implies that the negation of your proposition. So actually, if you can prove this, to be true, then this also is true, since a statement and its contrapositive, as I said before, are logically equivalent. To give an example for this, the second proof in assignment 2. So you were asked about this. If the intersection between A and its complement equal to phi, then this implies that A is the subset of B. That's kind of the reverse of the previous proof. So think about it in construction and contradiction. If you can't do that, you actually can, but I will not go through that. But if you couldn't, then maybe it would be helpful to try to prove the contrapositive of this statement. So what's the contrapositive of this statement? It's negated flip, so you will have A is not a subset of B. The negation of this implies that A intersection with B complement is not equal to phi. Okay, so if I can prove this to be true, then this statement is also true. Now from here, I'll just go as I did with previous proofs. I'll start by visualization. So I know that A is not a subset of B. This means that probably something like this, A, B, or maybe they are joint, so it will be something like this. And I'm trying to prove that B complement intersection with A is not equal to phi. So the B complement will be something like that. B complement, and here it will be something like that. Probably should change this to color black to be like this one. Doesn't really matter. Actually this should be included too. All of this is, so B complement is anything that is not B, so all of this is included. Now again, if you look at the diagrams, you can see that the statement is true. The intersection between B complement and A is not equal to phi for both cases if A and B are joint or disjoint. However, you kind of need to translate this to logic statements. So how I go with that? Again, I will just fall back to construction. From here I can say that there exists, let's choose another color. There exists an element X such that X is an element of A and X doesn't belong to B. I'm just using the properties from the assumption I made. So A is not a subset of B, then there must be an element X that belongs to A and doesn't belong to B. So from this diagram, it probably is here or here. This X is an element of A, it's not included in B. The same thing here. Okay. Second thing is that since this element is not an element of B, then X is an element of A and X is an element of B complement. X is not an element of B, then it must be an element of B complement. Now, since X belongs to A and it belongs to B complement, then it must belong to the intersection between both of them, right? X belongs to A and B complement. And you can see that from the diagram. The intersection between A and B complement here will be this part, everything that is included in A except this joint with B, and here it will be the whole circle of A. Now, this part will not be included. This part, for this part is included in B, then it's not included in B complement. So we reached that there exists an element X that belongs to the intersection between A and B complement. Hence, the intersection between A and B complement is not equal to phi, which is actually what we were trying to prove. Therefore, the statement is true. This statement is true. I can't really copy that. So since this statement is true, then its contrapositive, which is this one, is also true. So in proving by contraposition, you start by trying to prove with another techniques, because this is a hard one. Don't like jump into using proving by contradiction as your by contraposition as your first thought. You start by trying to prove by contradiction or construction. You can't. Then you try to prove the contrapositive of the thing that you are trying to prove. And if the contrapositive is true, then the original statement is also true, because a statement and its contrapositive are logically equivalent. The last thing I want to talk about is that why a statement and its contrapositive are actually equivalent to each other. Now, the last thing I want to talk about is that why a statement and its contrapositive are logically equivalent. And there is an easy answer for that. The simple answer is that you can show that using the truth table. If you build the truth table for both, if you have like a proposition and a conclusion, and you follow the truth table for each, you will find that B implies Q is the same thing as not Q implies not B. However, I find it a little bit hard to intuitively understand the truth table, either for the contrapositive or a normal statement. So one of the things that I want to talk about is how to intuitively understand this truth table. So let's consider any random statement. For example, all gardeners like the sun. That's some basic statement. Now, what this truth table actually means is that it decomposes this statement into 4 logical statements, which mean this statement can mean or kinda imply that if I have a group of people and I randomly choose some of these people, and these people that I chose are all gardeners, this means that all of them like the sun. So if I have this statement kinda mean if I have like a universe full of people, like let's assume these are people, and if all gardeners like the sun, this means that if I choose a random group of them, and by chance all of this group are gardeners, I know that this group also likes the sun. However, this statement can be interpreted in another way. It means that I can't choose a group of people that are gardeners and do not like the sun, because all gardeners like the sun. Hence, I can't choose gardeners that don't like the sun, right? So actually, these two rows actually are the more intuitive statements, actually, and you will find that they are more useful than the other two, hence why they are like in bold green. However, the statement also imply another two statements that we call vacuously true statement. Vacuously true, it means that they are true, but they are not very important actually in most cases. For example, let's consider this. All gardeners like the sun. This means that I can choose a random group of people that are not gardeners, but they also like the sun. For example, I'm not a gardener and I like the sun. And this one means that I can choose a random group of people that are not gardeners and do not like the sun. You will find that these two statements are not very useful because like all gardeners like the sun, hence in most cases you will be interested in gardeners and people who like the sun to make use of the statement. However, this statement also implies that there are some people who are not gardeners and don't like the sun. And you can actually do the same thing with the contrapositive statement. For example, let's consider the first statement. If you choose a group of people that are gardeners and like the sun, that's kind of similar to saying that I choose a group of people, or that if, let me think about that for a second. It kind of means that if I choose a group of people that do not like the sun, not Q, then this means that they are not gardeners, because if you are a gardener, you like the sun. And you can actually follow the same way of thinking with all four statements to see that a statement and its contrapositive is logically equivalent. I will not go through that. However, I just wanted to give you an intuition because I had a couple of questions on what's the meaning of this true statement. That's it for mathematical proofs. Just to summarize, you start by visualization. After that, you have three techniques that guide your thinking. Of course, you are not obliged to think this way. You don't want to have your thinking boxed in certain uh, way of thinking. However, if you feel like you are stuck, start by construction using the properties of the given statements you have. If you can't do that, start by just try contradiction. Assume that the conclusion you have is not true, and just try to manipulate the structures to reach a conclusion and to reach a contradiction. Sorry. Hence, the opposite of your conclusion is not true, then the original assumption is true. And the last technique is that proving by contraposition. Here you fail to do proof by construction or by contradiction. So you just ignore the statement you have and you are trying to prove its contrapositive. And after that, you say if the contrapositive is true, then the original statement is true. That's it. If you have any more questions, just send me an email. Thank you very much and have a good day.